All right, tangent problem. All right, so when I say tangent, what comes to mind? All right, you think of a tangent to a curve to be a line that touches a curve. All right. Um, I'm sure by now you all know that tangent touches a curve at exactly one point. That is the basic uh, definition of a tangent. Okay, let's see, for example, look at the figure there. You see the line T. It touches that circle there at exactly one point. So that is typically what we 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 call a tangent line. All right. But now I'll show you another diagram so that you see how things can quickly get very confusing. Now, if we look at the line, so we're looking at this line here. You see that line there? All it intersects this curve C still at one point, but do you agree that is typically not a tangent, all right? That is not, even though that's why we also need to be careful with the definition of tangent. We say touch our curve at exactly one point, but now we're seeing another line that intersects at exactly one point, but it's not necessarily a tangent, all right? Now look at the line T. Again, it intersects at the point P, but now it goes all the way there, it intersects again. So you see, it touches the curve more than once. So you see, there we go. That gives us, so the more complex the curve gets, the more complicated your definition of a tangent is going to look like. All right. But for now, when I talk of tangent, what you should have in mind is what I showed earlier, the one with the circle where it intersects at one point. So just think about that to be the tangent I'm talking about. All right. Okay. Example one, let's say find the equation of a tangent line to parabola y equals x squared at the point 1, 1. So x is 1, y is 1. Now, for you to find the equation of a tangent line, you need to be given 2 points, all right? Because that's how you're going to get the slope. In this case, I gave you just 1 point. How do we get the slope? So we would try and approximate the slope. So our given point is that point the P, which is 1, 1, and we guess another point Q, which is close to P. We call it X. Obviously, the output is going to be X squared because the function is Y equals to X squared. So for every input X, your output is going to be X squared. So using these 2 points, P and Q, we can find the slope. And if you remember, well, slope is change in Y over change in X. If we do that, you get something that looks like this. And if we guess Q to be the point 1.5 or 2.25, then you see you get a slope which is positive, all right? And take note, x cannot be 1 because x is 1 at the point P. We don't want the point P and Q to be exactly the same point. So we choose some different value for x, typically bigger than 1, so that we get a realistic slope. Now, if I construct some tables of values, so you see these are just table of values, notice what happens. So here I'm approaching 1 from the right. So I start from 2 and I'm decreasing gradually and I'm getting closer and close to 1. Look at what the slope there is. It's getting closer and closer to the value of 2. Okay, again, I'm approaching 1, but this time from the left. So I approach 1 from the left, that is from 0, coming close and close to 1, that's my value of x. Again, look at the output. It tells us that this already gives you an idea that the slope there has to be 2. All right. And how do we now write this? We say, therefore, as the point Q approaches the point P, the slope there is just m. In this case, we're talking about 2. The slope there is 2. All right. As x gets closer and closer to 1, this slope, remember, this was our definition of slope. This there is just equals to 2. All right. And now, very important, how do you get the equation of your tangent line? All right. The equation of your tangent line is we use the point slope equation, which is y minus y1 equals to m into x minus x1. So y minus y1 equals to m, which is the slope, into x minus x1. And if you simplify that, you just get y equals to 2x minus 1. That's the equation of the slope. All right. So you see now that by us trying to approximate the slope, we introduce the concept of limits. All right. Now let's visualize this diagram. See what happens. So this second line PQ, so the one that looks bluish, the second line PQ, if I move this point Q, if I take this point Q closer and closer to the point P, notice what happened. That second line actually gets closer and closer to this radius line here, which is T, all right, which is our tangent line that we're looking for. So to approximate our tangent line T very accurately, we need to try and bring this point Q as close to P as possible, all right? Notice it at this point, you see the two lines there almost coincide, all right? It means that the slope that you're getting is more or less the slope that we are looking for, all right? And you need to take note, we can approach the point from the left or the right. Suppose now our Q was chosen in this other side, we still approach Q in this direction, so we keep going down. Notice it, by the time we're somewhere there where Q is close to P, these two lines, they almost coincide, all right? Meaning that we're getting closer and closer to the correct slope. Now, what is the limit of a function? So everything I've been saying so far is just taking notes to the idea of limit, all right? To explain limit of a function, we're going to look at limits in general, all right? We're going to look at numerical and graphical methods. Let's start with this, this function there, so x squared minus x plus 2, and we're focusing on values where x approaches 2, so x is near 2. Let's see what happens. So I'm going to choose values of x close to 2. When I say near 2, it can be from the left or from the right. So whenever we're talking limits and we say we're approaching a number, there's two ways of approaching a number. We can approach it from the left or from the right. So we need to consider both situations. So let's see what the table looks like. You see, yeah, I'm approaching the number 2 from the left. So we increasing gradually from 1, we increase the decimal values right up to when we get close to 2. Look at the output. The output somewhere here tells you that it's more likely going to be 4, right? And how do you check if that is true? Again, you approach 2 now from there. So you start from 3, you start dropping slowly and get close and close to 2. See what happens? The output again tells you that it's approximately 4, right? So using this idea, we can conclude that actually as x approaches 2 from the left or the right, see there, getting 4, all right, 4 as you approach 2 from the left and the right. All right, if you just join in, please make sure you mute your mic unless you have a question to ask. So what do we say in limit notation? So look how we do it. We say limit as x approaches 2 of this function there, a parabolic function, is equal to 4. 2. Whenever I say the limit as x approaches the number a, technically I'm saying that is the limit as x approaches a from the left and the limit as x approaches a from the right. All right. So yes, when you saw in the table there, we looked at it from the right before we came to a conclusion. Very, very please can you mute your mic? I think there is someone's mic which is on. All right. the limit of a function. So let's look at the definition. So this is now the general definition of a limit of a function. We say the limit as x tends to a of f of x equals to L. What does this mean? It means the limit of f of x as x approaches a is equals to L. All right. When I say x approaches a, it means when we choose values of x slightly close to a and not actually a itself. So be careful. Whenever you use the word limit, you don't consider x at the point a itself. You just approach a from the left and the right, not necessarily at x equals to a. All right. And that's what they're telling you here at the bottom. So x is not equals to a. All right. Another notation, if you check in the textbook or if you have some other math textbook, you notice it, they'll write stuff like this. They'll either say the limit as x tends to a of f of x equals to L, or they'll write it this way. I like this notation. F of x tends to L as x approaches a. All right. So if you give me this or you give me this, they all mean the same thing. All right. F of x tends to L as x approaches a. I will be more than happy to give you your marks. All right. Let me enlarge this a little bit so that I get my point clear enough. This is what I was telling you before. So look at the first case. This case is a continuous case. There is no discontinuity, right? As x approaches a, so when you approach a from the right or from the left, notice it, you get the same value L. The output is L, all right? So when I say approach from the left, you walking along the graph. You come in that direction, and you come in from this direction. Where do you hit, or where are you going to intersect? You see there at the point L, you're going to get the same output from the left and the right. But now, look at B. Someone will say, but what is the need of this point here? You see there's a little dot there, all right? This dot is to tell you that f of a is actually down there, all right? It's not even part of the function. However, this shouldn't affect our limit. Why? Because I told you before, when you compute limits, do not consider x at the point A. So this dot here, we don't care about it. It doesn't change our answer for limit. All we're going to do is say, okay, if I follow the graph and I approach A from the right and I approach from the left, what point am I getting to? L. Again, the limit is still L. Now look at this one here. You see there at the point A, the function is undefined. If you see an open dot there, it means that the function is undefined at the point A. But again, this doesn't affect us, right? I'm sure everyone is now smiling because they know why it doesn't affect our limit, because we don't care at what happens at A exactly. We only care what happens at A from the left or from the right. Again, if I follow this graph, if I come in this direction and I come from this direction, I still end up having my output at L. All right. We don't care what happened at x equals to a. We don't need to evaluate x equals to a. All right. Now they say guess the value. Let me just zoom out a little bit. So guess the value of the limit as x tends to 1 of this whole function there. All right. Take note again, you're going to choose values of x close to 1, but not necessarily 1. All right. If you put x equals to 1 here, if you look at the bottom there, already you see there is a problem, right? The function is not defined at x equals to 1. If you put 1 there, you're going to have 0 over 0, which is undefined, all right? So hence, try and not evaluate the x at the point A, all right? So let's see. Again, these are table values. But take note, in my test, I will not expect you to be using table values because you can see why I'm not going to give you any mark. We see too many decimals, right? This is just for you to understand, all right? So in a typical test situation, I'll give you a limit that you can compute without necessarily drawing tables like this. This table is just to explain that if I approach 1, again, I'm approaching 1 from the left. You see, I'm getting close to 0.5 as my output. Again, if I approach 1 from the right, you see, I'm getting close to 0.5 again as my output. This tells you that typically your limit is equals to 0.5. All right. Graphically, so this first graph, we just change it a little bit. Remember that it was not defined at 1, all right? Because when we put 1 there, we try to divide by 0. But now I tell you that I change that function slightly, and I say at x equals to 1, my output is 2, all right? Again, it doesn't affect our limit, right? Because x equals to 1 gives me 2. I don't care about that. All I care about is this first situation. When dealing with limit, you're focusing on the point where x is not equal to 1. It means that it should be close to 1 from the left and to the right, but not necessarily equal to 1. Now, if you look at the sketch, at x1 itself, look, you get 2. 2 is a point that is completely out of the graph, all right? It's in no one's land. However, it doesn't affect our limit again because you see this arrow that's telling that when I push from the right and from the left, I'm getting towards 0.5. That is limit. All right, so that is the importance of limit. And if you understand every time you say up to now and then, you should be fine if I ask you a limit question. But we're going to see more examples. Now there's something called one-sided limit. If I say the limit as x approaches 1, already I assume that you're going to look at it from both sides, all right? But sometimes I can specify that evaluate the limit as x approaches maybe 1 from the right, all right, or from the left. That's now what we call one-sided limit. Oh, I see someone was asking a question. 2 doesn't contribute anything. The answer is when talking about limits, yes, 2 doesn't affect your limit. All right. So at x equals to 1, the output was 2, but you notice it was completely out of the graph, and we don't care about x equals to 2 because when dealing with limit, we don't look at the function at that point A itself. The only time where 2, the 2 you're talking about will be important is when we're discussing continuity. For now, we're just looking at limits. For limits, the number A itself, so x equals to A, we don't care about it. But when we discuss continuity, then okay, the number itself at that point, A, the function has to be valid. All right. But we're going to discuss continuity in the next class. All right. So for now, for limits, we don't care about 2. One-sided limit, so let's see. This is something called the Heaviside function. Heaviside function is what you guys normally call a step. For those doing physics engineering, I'm sure you must have come across step function at some point. But now the idea is when t tends to 0, you see the negative sign there means from the left. So keep in mind, if I write in a test limit as x approaches a number and I put a sign on top, plus or minus, minus simply means from the left, and the plus here simply means from the right, all right? And you can read it from the function. As t approaches 0 from the left, it means we're looking at this first piece there. You see your output there is 0. And as t approaches 0 from the right, it means it's strictly greater than or equal to 0. Therefore, your output is 1. And that's how they got this result here. All right. There they're just explaining what the minus and the plus sign means. So minus means you need value slightly less than 0, so approaching 0 from the left. Plus means value slightly greater than 0. Be careful, we need value slightly greater than, all right? If I say 0 from the right and you go and substitute 10, notice it, you're going to get completely different answer, all right? You need something really close to 0 from the right. And this is what one-sided, so we call this the left-hand limit of f of x. So when you are pushing a from the left, you see there's a to the minus there. And obviously, you know what's going to come next is a from the positive side now, approaching a from the positive side. Look at these two diagrams to explain what they're saying. Here they are pushing a from the left. You can see you getting when approaching, when I give you a sketch and I say what is the limit as x approaches a from the left, for example, you need to trace, you need to walk along the curve. So if I walk along the curve up to that point, you notice it, the output is L. And you saw I was walking the left direction of A. Now if I say X approaches A from the right, this one is from the right. Again, we're going to go in that direction. The output is going in that direction. And you notice it, you still get L. All right, so you see from the left and the right is the same. If the limit as X approaches A from the left is the same as the limit as X approaches A from the right, therefore the limit as X approaches A, we're just going to call it L. All right. But if these two limits are different, for example, if here I get L and here I get something else, then you say the limit as X approaches A does not exist. All right. So for a limit as X approaches a number A to exist, the limit from the left and from the right must exist and they must be the same. All right. And that's exactly what they're saying here. So this theorem here is very, very important. We're going to discuss it again when we discuss continuity. So limit as X approaches A is L if and only if these two conditions hold. The limit as you approach A from the left is exactly the same as the limit as you approach A from the right. You see the output is exactly the same. It's L in both cases. That is only when you're allowed to say that by conclusion, the limit as X approaches A of f of X is R. All right. Now we have an example here. This is something that you can be asked. It's a g function, g of x function. They say find the limit as x approaches 2 from the left. How do you do it? Again, this is 2. This is the point 2. I'm approaches 2 from the left. It means I'm going to be walking along this line. There we go. Once I hit 2, what output do I get? 3. There we go. Your answer is 3. Easy. Now they say 2 from the right. Now, if this is 2, then from the right means I'll be moving in this direction. And what output do I get? I get 1. And what then do we say for C? The limit as x approaches 2. Because the limit as x approaches 2 from the left and the right are different, we say that this limit does not exist. All right, so the limit as x approaches 2 of g of x does not exist, because when we move towards 2 from the left and the right, we get completely different result. Now let's try for 5. The limit as x approaches 5 from the left. So take note, this is 5. From the left means I'm somewhere there. I'm going this direction. And once I hit 5, I read the output. I get 2. All right, you get some answer the 2. And 5 from the right means you start from this side, you come, once you hit 5, you read again is 2. You see from the left and the right is 2. The limit as x tends to 5 is going to be 2. Why? Because from the left it was 2 and from the right it was 2. Now if you notice it, when x equals to 5, you get some funny result, 1 point something. Again, you see that didn't affect our limit at all because we don't care about what happened at the point 5 itself. We just care about what happened at values closer to 5 from the left and the right. All right. And here they're just giving out the explanation, which I've already done. Now, infinite limits. Now, you need to be careful. When I use the term, the limit does not exist, there's two possibilities. The first possibility is because the limit as we approach the number a from the left is different from the limit as we approach that number from the right. But now, we're going to hit infinite limits where you compute a limit and then you get infinity or minus infinity. And you need to take note, the word infinity is not actually a number. So in a test, if you solve for a limit, it gives you infinity, you need to tell me that, therefore it does not exist, all right? So if the limit is infinity, it means it does not exist, all right? Because you're not converging to a particular number. It's growing infinitely, therefore the limit does not exist. So infinite limit means limits that technically they don't exist, okay? So let's look at the definition. Now, as x approaches a, my function is very huge, all right? My function f of x is infinity. Infinity means it's so huge, all right? So it gets big and bigger, it keeps getting bigger, it's going forever. And in summary, we say f of x approaches infinity as x approaches a, all right? I'll mention one more time, infinity is not a number. Someone asks you what is infinity, Don't go tell them that it's a billion. No, infinity is not a number. All right. If you say a billion, I'll ask you, how about a billion and one? Which of those are bigger? Because you can't tell me which number is the biggest number, therefore infinity we can't quantify as a number. All right. Yeah, this is explain it in words, what I've already said. And let's look at it graphically. You see, when I approach x equals to, so this is a there. When you approach a from the left, it means you walk along the graph. You see, you're heading towards infinity. You're not heading towards some number. You're just going infinitely large. All right. The same thing happens when you approach a from the right. You see, again, you're going towards infinity. All right. It doesn't converge to a specific number. So we say the limit as x tends to f of x is infinity, or just tell me that the limit does not exist. All right. And you can also get negative infinity. So in this case, when we approach a from the left, you see heading towards minus infinity, and you approach from the right, again, you're going towards minus infinity. So again, minus infinity, like I said, is not a number. It's just a number that is too very large, but in a negative direction. All right. All right, let's look at an example. The limit as x tends to 0 of minus 1 over x squared. All right. Remember, as x approaches 0, this function here is getting very, very big. All right. If you check on the textbook, there is a table there that explains to you why it gets big. You can already think about it. If I choose a number slightly, so a number close to 0, let's say from the right, for example. All right. So let's choose not point not 1. Do you agree that those are so many zeros? And once you take reciprocal of not point not 1, you head into 10 to the power. So you're looking at 10 to the power 5. So think about having not point not 20 times 1. That is 10 to the power 20. See, the closer you get to 0, the infinitely large your output is going to be. But now, why do we have minus? We know it is going to be infinity. If you can spot that it's going to be infinity, notice it, you divide it by 0, by the way. If you put in 0, there is infinity, right? It's undefined. So 1 over 0 is undefined. 1 over 0, if you punch your calculator, it shows you error. That error there is because the calculator doesn't know infinity. The calculator only knows numbers, all right, actual numbers. So minus sign is because of this negative here, all right? And you know already that this piece here, 1 over x squared, will hit infinity, but because of this minus outside here, it's going to be minus infinity now, all right? These are all the possibilities you can get for infinite limit, so one-sided infinite limit. So the limit as x approaches a from the left can be infinity, from the right is infinity, from the left is minus infinity, from the right is minus infinity. All right, someone said they don't understand. What don't you understand? The previous question. So we look at you talking about this one. Well, I'm going to explain it again. So here there's a table. There's a table here that is actually missing. All right. This is just a summary of what you're going to get. Now, when x approaches 0, whether you take it from the left or the right, take note, because of this square, a negative value square will end up being positive. And I mentioned before, if I give you 1 divided by 0.1, what do you get? You get 10. Take note that's 0.1, and 0.1 is far away from naught. It's too big. Now let's choose 0.01. So we're trying to take a number close to 0 from the right. 0.01, 1, the reciprocal of that you see is 100. So if you keep using very small decimal values, you end into infinity. All right. Be careful in a test. I expect you to just look at this and tell me the output, not necessarily put a table and use a calculator, right? You don't need a calculator. I told you before, I'm going to give you questions that will not require a calculator. So you should be able to compute them without using a calculator, all right? I've already discussed this. Now let's see what happens here. So they just showing us graphically what this means. When x approaches from the left, you see that we're getting towards positive infinity. When x approaches a from the right, again you're approaching positive infinity. When x approaches a now from the left, this time we're heading towards negative infinity. So these are all the possibilities you can get. All right. So for limits at infinity, you get four possibilities. All right. So either you are pushing the number from the left and you're going to positive infinity, or you are pushing the number from the left and going negative infinity, or you are pushing the number from the right and going to positive infinity, or are pushing the number from the right and going towards negative infinity. All right. These are all the possibilities. Again, now this is something really important. If you take the limit as x approaches a number and you get infinity, therefore x equals to that number is called a vertical asymptote. All right. So the line x equals to a is called a vertical asymptote of the curve y equals to f of x, provided only one of these entire statements needs to be true. If you approach a from the left or from the right, or from the left or from the right, and you get it infinity or negative infinity, that number there is called vertical asymptote. All right. So if I give you a limit and your answer is infinity or minus infinity, then I say, what can you tell me at x equals to a? You tell me that is actually vertical asymptote. Now they say find vertical asymptotes of f of x equals to tan x. Remember, if you plot a graph of tan x, you're going to have problems at power over 2, 3 power over 2, and so on. So odd multiples of power 2, you notice tan is undefined at that point. Where is that coming from? It's coming from the fact that tan is sine over cos, and wherever cos gives us 0, we're going to have a problem because we can divide by 0. So whenever cos is 0, you're going to divide by 0. All right. Now let's see. The first one you're going to hit is at pi over 2. So either pi over 2 from the right or the left. There cos of pi over 2 is 0. You'll be dividing by 0, which is a problem. At 3 pi over 2, you still have a problem. You can see that they're telling you pi over 2 from the left or pi over 2 from the right. You get infinity and minus infinity. All right. And if you keep going, so this is just a sketch of tan. This line that you see here, that looks, I'll call it purplish because this is not red. So these lines that you see here are the asymptotes, all right? Asymptote, I'm just going to explain again what asymptote, so that when you see it, you're going to quickly recognize what asymptote is. So your curve gets close and close to this line called an asymptote, but it doesn't actually cross it. All right. You see, this curve does not cross the asymptote. It just gets close and close to the asymptote, either on the positive side or from the negative side. All right. And what all the asymptotes are, like I said, if you take odd multiples of pi over 2, you will get your asymptote. So if n is 0, you have pi over 2. If n is 1, you have 3 pi over 2, and so on. For those odd multiples of pi over 2, you will definitely hit an asymptote. It means tan will be undefined. You either get infinity or negative infinity. All right. It looks like this was the last slide. Any questions so far in the introduction to limits? All right. If you have no question regarding limits, any question regarding the assignment, obviously we can discuss that only after everyone is done submitting. That we can discuss that. Since we don't have a class for your test, so obviously I'll upload a memo. You look at your work and then you compare them. And if you have a question, you can ask me. Any question regarding your semester test? All right, your assignment you need to upload on Blackboard. All right, I see, Baloyi, you were one of the students that recently got registered, so you have to upload on Blackboard. If you complete the honesty declaration, the test link is going to appear, and once it appears, the assignment link, follow the instruction. They click on the ball link. You scroll down, there'll be something that says browse to find your PDF, and then you attach it to some. Everything must be submitted on emails. If someone emails me the document, it means that they didn't read the instruction, and they will simply get a 0. All right. Someone says, how many questions? I'm not sure what you're trying to ask. How many questions for what? If you have the assignment, obviously you know how many questions are there. The semester test. All right, the semester test. At the moment, we're still moving forward and backward regarding moderation. But I can guarantee you, it's not about how many questions, because I can say that you have 5 questions, but each question has an A, B, and C. All right, so how do you count that? So I'm reducing the number of A, B's, and so on, just so that you have numbers like 1, 2, 3, and so on. But typically, it will be not so many questions. It will not be so many questions. It will be questions that you can do within the time frame. Be careful. It will not be like a test you've done before online, because usually we give you guys infinite amount of hours, but it's not going to happen anymore. You have 2 hours and a half. If any changes happens in respect to the time, because we're going to discuss in the meeting tomorrow, then I might increase it slightly. But for now, keep in mind it's 2 hours and a half. The normal test time is 1 hour and a half. We say because of lockdown condition, we add in extra 1 hour. So your semester test or your semester test is going to be 2 hours and a half strictly. And obviously, you can guess what's going to happen in the exam as well. The exam is usually 2 hours, but because of lockdown, we added extra 1 hour for you to scan and upload and stuff like that. So you're going to have 3 hours for your exam. But for your semester test, I've said already, it's 2 hours and a half. So don't spend time looking at stuff, reading the textbook, or doing funny stuff. Write what you can write. Scan as early as possible, submit, because if you fail to submit on time or the link disappears and you haven't yet handed in your work, obviously that is straight 0. All right. We had a number of situations last semester. We don't want it to happen again. Any other question? All right. If there's no other question, I'm just going to stop.